Answer the following questions about glucose, C6H12O6, an important biochemical energy source. Write the empirical formula of glucose. Okay, the first thing you got to remember is that the empirical formula may or may not be the real formula. Basically, the empirical formula is the simplest whole number ratio between the elements in the compound. So if you come up here, C6H12O6, 6 and 12 and 6 have a common factor of 6. And if you pull that out, if you think of factoring like you learned in algebra, you pull a 6 out of 6, what's left? A 1. You pull a 6 out of 12, what's left? A 2. You pull a 6 out of 6, what's left? A 1. And so the empirical formula is CH2O. That's it. That's the simplest whole number ratio. That easy. In many organisms, glucose is oxidized to carbon dioxide and water, as represented by the following equation. So glucose, and then this is actually what happens in the body. Glucose is the food the cell uses, and you breathe in oxygen and converts it over to carbon dioxide. That's what you exhale, and water, and that's what your kidneys take care of, getting rid of that kind of stuff. And so you have 2.5 gram sample of glucose. So this is 2.5 grams, and it's placed in a calorimeter. And after the reaction is initiated and proceed to completion, the total heat released was 39 kilojoules. Calculate the value of H naught in kilojoules per mole for the consumption or the combustion of glucose. Basically, it released 30. This is a weird problem. It's so easy. Kids sometimes don't know how to do it. 39 kilojoules of energy were released when you burned 2.50 grams of glucose. And if we did this problem right now, the units would be kilojoules per gram. We don't want kilojoules per gram. We want to convert grams to moles, which we've done a bazillion times in here. So glucose, you got 6 times 12.01, and then you got 12 times 1.008, and then you got 6 times 16. And when you do this on a calculator, you end up with 180.156 grams per mole. And remember, when you add, you count sig figs or decimal places. So this one has 2, this one has 3, this one has 2. So basically, best answer on the AP exam is 180.16 grams per mole. And so then we come over here, kind of jammed us for time, but because grams is on the bottom, the 180.16 grams would go up and the 1 mole goes down. And now it's that easy. We're in kilojoules per mole. Try not to make this any tougher than it is. When I do this on the calculator, I end up with 2,810.496 kilojoules per mole. That's way too many sig figs. This has 3, this has 3, this has 5. Best answer is 2,810 kilojoules per mole. Okay, let me grab an eraser because that kind of looks like a 6. And then I should probably look at the scoring guidelines, but because this is an exothermic reaction. It releases energy, and that's the energy that allows you to walk and allows your heart to beat. People that starve to death and don't take any glucose, they eventually die. And it should be negative just because of the word heat released, or just say 2,810 kilojoules per mole of energy will be released. Okay, so either say the word or make it negative, whichever you prefer. C, when oxygen is not available, glucose can be oxidized by fermentation. In that process, ethanol and carbon dioxide are produced, as represented by the following equation. So here's the equation. Sorry. Oh, I'm not using my pen. Let me use my pen and not try to write with the mouse. So here's the equation right here. And then here's the delta H. And now this is still the old notation because this is 2011, but now you would see something like 68.0 kilojoules per mole RXN, meaning 1 mole of this and 2 moles of this. And so the first question is, what is the value of the free energy change? So changes. So they want delta G. What is, oops. Okay, so what is delta G naught? Now, we have an equation that relates delta G and K. Girls are not real tough when they're having kids naturally. Negative. In thermal, we always use this value of R, 8.314 joules per mole K. If you guys look at the scoring guidelines in 2011 on the formula sheet, this was only given to 3 sig figs. They now give it to 4. The temperature is right here. It's 298 K. Boom, boom. And then we have to take the ln of 8.9 times 10 to the 39th. Okay, now I have a problem here. I'm going to tell you what I think the answer is, and you've got to be comfortable that this is not the answer on the scoring guidelines. My calculator says 227,904.0932. Sorry, guys, my mic is rubbing in my face. I hope this doesn't sound bad. Joules per mole. And remember, I should probably just do this up here. Delta H and delta G are almost always in kilojoule. It's delta S that is in joules. So there's 1,000 joules in a kilojoule. And if I do that, now here's what I think. This number has 4 sig figs. This number has 3. This number has 2. And in actuality, remember, the numbers all after the decimal point are the only ones that count. I mean, this is crazy. You can make an argument for 2 or 1, but they're keeping 3 on the scoring guidelines. And maybe that's because of the rule, always keep 3, because then you'll never get wrong. But in my opinion, the best answer is 230 kilojoules per mole. What do the scoring guidelines have? Negative 228 kilojoules per mole, which is what this is rounded to 3 sig figs. I don't know why they think we get 3. It looks to me like we only get 2. I would take either of these answers. Then calculate the value of the entropy change in joules per mole K at 298. And so this one, now, here's what you got to get. They gave us, sorry, we're on this one. They gave us delta H right here. And we just solved for delta G right here. Or right here. Whichever one you use is fine. Okay, so here's the deal. Here's the equation. Gators are hell without tartar sauce. Now, we know this, and this, and this. This is the unknown. So I'm going to swing this guy over here because then T delta S will be positive. And I'm going to swing this guy over here. And so then I get T delta S equals delta H naught is where it was minus delta G naught. I don't care how you do this. You can add T delta S to both sides. You can subtract delta G from both sides. I don't care how you do this. So this cancels this, and this cancels this, and you end up with T delta S. And then we're solving for delta S, so we divide by T. And so I will do it like the scoring guidelines did it. They told you in the problem that delta H is negative 68.0 kilojoules per mole. And then we just figured out that delta, so again, that's where I'm getting that. Delta H is negative 68. I don't care which one you use. It's probably not a bad idea to do this because when you take the test, I'm going to hammer on you. Always keep 3 sig figs. Always keep 3 sig figs. It's one less thing to worry about. And so minus negative 228 kilojoules per mole. And remember, you can't add and subtract unless the units are the same. And then instead of dividing by T, I'm going to multiply by the reciprocal of T. And order of operations, so this is going to be negative 68 plus 228 divided by 298. And when I do that, I end up with 0.537 kilojoules. Because remember, when you subtract, you have to have the same unit per mole K, because K is downstairs. But it specifically asks for joules per mole K. So then 1 kilojoule goes down is 1,000 joules goes up. And so if you do that, you get 537 joules per mole K. And again, keep in mind, my bias is we should only have 2 sig figs. This should have been 230, blah, 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 but just keep 3. Indicate whether the equilibrium constant for the fermentation reaction increases, decreases, or remains the same if the temperature is increased. This is kind of interesting. Let me write this down again. So, sorry, I already made a mistake. So here's what happens. C6H12O6, which is glucose. If there's no oxygen to react with, it becomes this, and I'm looking at this, they say liquid, and then this is gas. All right, and so what happens is, will the equilibrium constant for the fermentation reaction increase and decrease if, or remain the same if the temperatures increase? Well, remember, they told you that delta H naught was negative 68 kilojoules per mole, which means this reaction is exothermic, meaning heat's going to exit or heat is a product. So heat actually goes here. And so this is a Le Chatelier's principle. And I'm going to do the problem, and then we're going to go back. Principle, I hope I spelled that right. Okay, so what happens if you increase the temperature? It doesn't like that you increase the temperature. I suppose I don't need these parentheses here. It doesn't like that you increase the temperature. It tries to undo that stress by becoming colder, and this causes it to shift left. And because it shifts left, Kp decreases. Why? Because equilibrium constant is the stuff on the right, to some power, over the stuff on the left to some power. And if the right is going up and the left is going down, if the right is going down and the left is going up, the equilibrium constant would decrease. Now, that's the thing, but remember on the AP exam, always answer the question first. This is kind of your work. And then, will the equilibrium constant for fermentation, that's this reaction, increase, decrease, or remain the same? I'm going to switch colors. You got to answer the question first. So I'm going to come down here and I'm going to come down here, draw a line, and say the equilibrium constant would decrease. Always answer the question in the first sentence. And then here's your justification. I was just doing this to explain to you. If the temperature is increased. The equilibrium shifts to the left, decreasing the equilibrium constant. All right. Finally, using your answers for part B and part C, calculate H for the following reaction. Okay, so this is interesting. I get such a kick out of this. This is a Hess's law problem. So here's the deal. I'm going to do all kinds of equations. This, I'm dropping physical states. This is the equation that was given in part, well, way at the top, actually even before A. So the equation that was given, grab the eraser, sorry about that. And so this was the equation given first in this problem. Now remember, I'm dropping physical states, and then delta H reaction is negative 2810 kilojoules per mole. We actually solved that in A. Switching to purple, then we got C6H12O6. If there's not oxygen, then it does this reaction. And then delta H for that was negative 68 kilojoules per mole. And now I'm going to switch to blue. Okay, so now I need to take what I would call equation 1 and equation 2 and rewrite them and see if I can get this. Now, here's what I do first. C2H5OH. I need that to be on the left. Down here, it's on the right. So A, it's on the wrong side, and B, the stoichiometry is wrong. So what I'm going to do is I'm going to take equation 2 and I'm going to flip it and divide it by 2. So half of 2 is 1. Half of 2 is 1. Half of 1 is a half. And then I'm going to take this equation and flip it. That makes it positive 68. And then I'm going to divide it by 2. Now, interesting, this is in the right position, and I've used this equation. And remember, you can only use them once. Now, I need to have an O2 on the left with the 3 in front of it. We've already used this equation. I only have one equation left. Okay, so the O is in the right, it's on the correct side, but again, I have to divide it by 2. And so when I take this, 1 divided by 2 is a half. 6 divided by 2 is 3. That's good, because then this will be correct. 6 divided by 2 is 3. I did something wrong here. Yeah, this is supposed to be a 6. I don't know why I put a 3 there. And then 6 divided by 2 is 3. And so I didn't flip this, so it's still negative, but I did divide it by 2. And so the interesting thing happens when you add these two equations together. Half a mole of this cancels with half a mole of that. That's gone, and that's good, because if you look up here, there is no glucose in this equation. I have 1 carbon dioxide on the left and 3 carbon dioxides on the right. So all of this goes, and one of these, and this changes to a 2. And so then you get C2H5OH plus 3O2 goes to 2CO2 plus 3H2O. And then I have to add, this would be positive, I don't know what this is, but when you do this on the calculator, 68 2.0 divided by 2 plus negative 2810 divided by 2, you end up with negative 1370 kilojoules per mole. Sorry, I don't know what I did there. And I think that is the end of this problem. Good problem, though, because it's got Hess's law in it. All right.